Yeah, so welcome everyone. As most of you probably know, cryptography underpins, at least technically, the security of our data and communications by providing methods and algorithms to provide protection in untrusted settings. However, for this to actually work, these methods and algorithms should actually provide the security that we want them to provide. And we should build confidence in that before we actually deploy these methods. And this is quite difficult because there's many moving parts to cryptography, and the sort of confidence we build in its security relies on a long chain of reasoning and a long and complex chain of reasoning. And so this brings me sort of to the main underlying idea or message of this talk. And this topic is that machine check reasoning can help increase the confidence across the cryptographic spectrum. Okay, and so the spectrum at a high level, when I'm talking about, can be seen as follows. So when we design cryptography on the very low level, basic level, we have our hard assumptions, which are the mathematical problems that we deem to be hard or feasible to solve with our computer. And so then we use these hard assumptions to design our primitives and schemes, which are essentially the cryptographic building blocks. So these are one or several algorithms that are meant to specific cryptographic tasks. And then in turn, we use these primitives and schemes to build or design our protocols, which are essentially the message sequences or interactions between parties to establish or start communicating in a secure manner with a definition of security that depends on the context. So but then eventually we have to actually implement this design and these schemes and protocols to actually run it, of course. And yeah, so this is essentially the spectrum that I'm considering now on a high level. This is of course abstracting away quite a bit, but this is what I will be considering. And then across this spectrum and these different parts, we have different techniques and approaches to sort of gain confidence in that what we are doing is actually correct, and this provides security that we want. So, for example, as we're starting at the lowest level of the design here, and that would be hardest assumptions, we have cryptanalysis, which essentially just tries to tries to find the best attack against the mathematical problems or best solutions, and then justify thereby that these are actually sufficiently hard to solve to build a cryptography. Then for the design of the primitive schemes and the protocols, we have mathematical proofs, essentially, showing that they provide the security that we want them to provide. So we sort of specify the protocols and primitives in a mathematical or algorithmic way, and then provide the proof. And for the implementation part, then there's you can sort of look at it in two sort of separate parts, where the realization of the specification by the implementation is mostly done through testing of input-output behavior, whether the inputs are validated properly, and this kind of testing analysis. And then on the implementation level itself, there's still the question of whether the implementations don't exhibit observable behavior inside their execution environment, essentially, which could be secrets during execution that are not typically abstracted away or not accounted for on the specification level. Right, so despite all these methods and approaches that we have in trying to establish confidence, there are still things that can and do go wrong at all levels. And so, for example, for the proofs that we have on the specification level, or the protocols and primitives, well, the proof could be wrong in itself, or alternatively, the proof may be not exactly applied to what we had, to the actual thing that we end up deploying, or it did apply once, but then the actual thing developed and the proof doesn't apply anymore. And so there are several or numerous examples of these are similar things, but these are some relatively recent ones. And some of them, sometimes, like the proof can be wrong, and it's really just like a proof issue. So this would be the case for Sync Plus, for example, provide and wire, where eventually you can simply fix proofs so that there's no real world attack or problem. Well, in other cases, which is the case for the other two, there's actually also then, well, the proof was thought to be correct for a very long time, then it turned out to not be correct, and extra attacks, corresponding attacks in the real world secret extraction was possible. So then on the implementation side of things, on the technical side, when we try to see whether the implementation properly realizes the specification, we typically do this, as I said, by sort of testing and analysis, but typically, like, you cannot test, this is incomplete because you cannot test all input-output behavior because there's too much. And so this can lead to, well, not testing for certain behaviors that might be bugs or problematic in the end. And so these are two examples here that are relatively recent, where in the first one there was no proper input validation on the implementation level, leading to again extraction of secrets. And in the second one, not really a concrete attacks that were possible, but still the implementation misbehaved for certain inputs that were not in the testing set. And so finally for the side channels, well, this is also similarly typically sort of incomplete testing, which cannot test for all sort of possible environments that will be executed in. And this can lead to then, for example, here these two examples, side channels, leaks of secrets to dynamic differences when using the secret as an input to your operations. Certain dynamic differences then can lead to secret extraction. So, as these examples sort of show, things, despite having these methods and approaches to gain confidence, things can and do still go wrong. Because cryptography has many parts, and it is quite complex to, well, even on an individual part already do this properly, but also then combining the whole thing is complex and rather, especially because, for example, for the proofs, this is typically handwritten and manual process. And for the testing, also often referred to pen and paper methods. And the testing, as I said, is often incomplete and cannot cover all cases. And so this makes the whole process only given a higher likelihood of failures. And so in recent years, tools and frameworks have been developed for use on the computer that allow to use the computer to actually verify the reasoning that we do, and for the proofs then mostly, and also for the testing place, sort of testing, also by reasoning about the implementation, sort of mathematically proving that it satisfies a certain specification for all inputs. I think this is also called computer-aided cryptography sometimes. So back to the spectrum that I quickly sketched in the beginning, and let's look at a specific, sort of specific parts now, where we see exactly or how it can be used and where it is used. So for protocols, so let's start with the protocols and their design. So a protocol, like very generically, typically used as follows, where we have two communicating parties that communicate by sending each other messages that are at least in part computed from the cryptographic primitives that the protocol employs. And so then the aim of this is achieving a certain security guarantee that depends on the context, of course, and this assumes it is then assuming the certain appropriate properties of the primitive. And in a typical proof, we actually, or scenario model, we actually consider the adversary to be sort of have control over the whole network, so it can view all messages, see all messages, inject messages, alter messages. And so the question is whether the message sequence like this can actually provides the required security guarantees. And so also typically for protocols, we are interested in a setting where there's like multiple simultaneous or composed sessions, because this matches what typically what we have in the real world, where there's many people using the protocol simultaneously. And also potentially with some other parties in certain instances of the protocol. And so that understanding security guarantees really depend on the depend on the context, but to give you a quick example, quick ideas, so we have the fundamental ones, of course, that are like the confidentiality in our application, that most people will know confidentiality referring to only the right honest parties can see collected data, and authentication that the honest parties know who the document. And some more sort of advanced or specific protocol-specific properties are these more temporal properties in forward secrecy and post-compromise security, where it is about either past communication remaining secure after compromise, or the security sort of healing or recovering after compromise. And then we also have more privacy or surveillance-related properties that you can consider in, for example, anonymity and deniability, which is about, in the case of anonymity, the infeasibility sort of identifying communicating partners from outside, and deniability of not being able to prove, or the transcript, even if someone participated in a communication or protocol, then the transcript does not provide actual proof with your party that this is that they participate. Okay, so for then the actual proofs that we do, and particularly the machine check proofs, there is two different models that we consider. And these models, the main difference between them is essentially the granularity of the attacker and the primitives that goes hand in hand that are models, and so consequently the guarantees and sort of scale that we can prove models at is different as well. And so specifically sort of how you can look at it is that in the symbolic model, we model the adversary by explicitly specifying the allowed behavior and computation that we can do. While in computational model, we explicitly deny behavior, so we allow everything, but then deny a specific unreasonable or we deem unreasonable computations. And so similarly, or relatedly, I should say, the primitives in the symbolic model are less precise, more like realized, more like black box operations that so they are just not as, but they don't specify complete computation that actually happens in real life. While in the computational model, this is more, exactly as it is, as it would be more accurate to the actual computation that is being performed. And so from this, the rest of follows the guarantees in the symbolic model are weaker, because exactly because the adversary is allowed to do sort of this. And the adversary to weaken it. And the opposite in the computational model. But then for scale, on the other hand, we are able to prove large sort of properties and models that we are interested in the computational or in the full protocols, as I showed with the many sessions and color parties, and this is very large scale essentially. But the symbolic model then allows for a lot of automation and thereby you're able to scale. While in the computation model, this is exactly because of the fact that it's more precise and not possible, not as easy. And so there's many tools on both ends, but the most sort of prevalent at the moment in the symbolic model are prevalent already, and the computational model Cryptography. And these have then also been used in quite some high-profile sort of case studies, which for them, for example, has been used throughout at least part of the design and drafting phase for TLS 1.3, and actually also sort of in this process discovered throughout the class mistakes or errors or attacks that were discovered by hand, and thereby sort of informed updates to the overall protocol, and we can be sort of increase the confidence in the actual design. Similarly, for another example here, the other tools is for signal post-quantum digital exchange. That was at the beginning when establishing a communication channel. And this was actually after the design phase or drafting phase. This was sort of formally analyzed in both programming and cryptography. And also here, as with sort of TLS, they discovered certain properties that were assumed not well, were still needed on the primitives, as well as certain attacks in the protocol sort of sequencing that were not discovered by hand or before. Right. So then, that's the sort of short overview for protocols and tools. So now I will consider the primitives and implementations simultaneously, because I want to also sort of cover the bridge between these two sort of layers, where for the realization of the primitive. So if we now look at this, this is a specific part here of the spectrum, then what we are interested in here on the primitive level itself, or the steep level, is whether it's correct shape, where correct is a relatively basic property usually, you just like computes the right thing in an almost environment. But security obviously, like again, depends on the actual primitive scheme and context, and so two basic examples, of course, are encryption and signatures, where for encryption you want something along the lines of it being feasible to extract information from the thing that is encrypted, and for signatures that no one can impersonate you or like a party or send messages on behalf of them. And for the actual the bridge between implementation and specification here for the primitives, we are of course interested whether this realization is actually faithful to its specification, so whether the implementation actually matches the specification. And again, as I mentioned in the beginning as well, on the implementation level, we're also interested in the side channel attacks, this physical observable behavior that is dependent on the execution environment. And importantly for implementations, this should all sort of hold for full optimization, because usually for a basic reference implementation, this is relatively, well, it's easier to show, of course, because the implementation logic is typically less complex. But eventually we want to deploy we want to get a piece of the thing we deploy, so this should all go through after optimization as well. Right, and so now I want to sort of focus on one specific toolchain, yeah, which is the EasyCrypt and Jasmine, which is the toolchain that is used by Forza. And so EasyCrypt and Jasmine are tools that are sort of have an integration and bridges this gap that I'm talking about between implementation and specification. So EasyCrypt is a sort of proof assistant, or a building proof, that essentially means that you can perform the mathematical reasoning by computers. And it's aimed at core protocols, while Jasmine is an implementation framework that is aimed at implementing highly optimized cryptography. And so the typical workflow here, when you have like a primitive scheme that you want to implement, is you would specify in EasyCrypt in a mathematical way, as you usually do on Pedagogy as well. But then you use the tool to machine check your proofs. So the proofs that we usually have on Pedagogy, we now do in the tool and then check the whole sort of reasoning, and so thereby we establish the correctness and security in the tool. And then on the other hand, we have the implementation in Jasmine, which we code, as we do when we implement stuff. And Jasmine, the framework actually provides certain automated tool checkers that for this source implementation prove the safety and the constant time behavior of the implementation. So the safety here essentially boils down to the semantics being well defined, so there's no undefined behavior, so it behaves as expected essentially. And the constant time is exactly this specific side channel that I showed, like the examples of the failures with where there's observable timing differences based on secret values, which allows you to extract secrets, which this proves is not, which these tools then show is not full of the case for this implementation. Then it depends on these kind of timing, more these timing differences, or at least doesn't use these instructions, I should say. And so then we compile it down to assembly, as we also usually do when we have implemented something. But as opposed to typical compilers like the C compiler, this compiler has been also verified separately to actually maintain the things that you care about for cryptographic implementation, or at least some of these properties that are listed there. So in particular, the package and constant time, which, for example, for every other regular general purpose language is not the case. So for example, C has no, the C compilers have typically no guarantees that they maintain any form of constant time property. Right, and then now, so the bridge, this is where the bridge community comes in. The Jasmine framework also provides a tool for extracting a model of your implementation from Jasmine to EasyCrypt. And then at that point you have your implementation essentially in EasyCrypt, and you can again use the tool to formally prove, machine check the reasoning of your proof that the implementation actually matches the specification on which you did the security proof, and thereby sort of transfer the guarantees to the implementation. Right. So then for this specific tool chain that has been pretty successful, I would say, in recent years. We have become pretty decent at doing stuff. So a couple of examples here, which I won't go into detail, but essentially I'll follow this workflow that I just said and just completed it in Yes, for Kaido and Hocken, which is the recent centralized post-quantum camera list. We have Shadow as well, for example, the hash function that is also standardized and widely used, as well as XMSS, which is a post-quantum signature, also standardized. Yeah. So for all of these, actually, we have the whole sort of workflow that I just described, and including optimized implementations, except for XMSS, which doesn't have an optimized implementation yet, but it is being worked on. Yeah. But if you have an optimized implementation, I guess I should add this to the previous workflow. So you first typically do this for a reference implementation, and then afterwards you optimize your implementation and you make sure the proof still sort of goes through, you update your proof. Yeah. Right, so now a sort of typical question that comes up is, okay, that's very nice, this workflow, and nice to see you do stuff, but in practice, no one uses this specific sort of language or tools, and you might want to actually adopt these tools or commit to these tools if you're just like programming or having your software in C or Rust or whatever language you use. And so a sort of mid-way solution here is there's a library of sort of formalized and implemented primitives that have also, which also this whole workflow has been sort of connected. Yes, so this is essentially for multiple primitives, among which ones that I listed here before as an example. And so then this library, this provides the whole development, but in particular the assembly. And so if you're going then, if you use sort of the same platform or architecture, then you can sort of integrate it there, which is sort of like well, solution to not adopt the whole toolchain. Right, so then finally, I've now discussed or shown you a specific sort of set of tools here, the most someone, the easy adjustment, and also the implementation. But the both ends of the both ends of the spectrum, yeah, on the primitive design and implementation side, there's manual tools, which we use for this purpose. So for this primitive, these are all tools that do similar things to easy represent data, allow you to specify your specification, your scheme, your primitive, and then formally push security. And on the implementation side, there's also many tools, and some of them, well, mostly they stay within this implementation lane, but some of them go, yeah, so some of them mostly stay in the implementation lane, some allow them to also prove functional patterns, but mostly implementation. But this branch that is also like important, that I just started to use in adjustment. There's not many alternatives, so I put a question mark here. There's like some decent combinations of tools that should technically allow you to do this, but yeah, not many actual use cases that have been sort of probably formalized and implemented and bridged together. And so then for future work, we sort of tie it in more with the subject of this conference, is that we got quite decent at doing this stuff, mostly for the fundamental things too. So the confidentiality, authentication, some of the related properties and protocols, but the more advanced properties for specifically the anti-surveillance or privacy properties, we don't really have much work on that yet. And these also seem to be, well, I haven't looked into it in too much detail, but they seem to be a different kind of approach needed. And so from our experience, this requires, well, discussions and conversations and collaboration between the actual privacy surveillance property experts as well as tool experts to see how to best formalize and recognize these properties. So yeah, work there still needed. And yeah, I want to leave it at that.
So, yeah, any questions?
Thanks. Thank you. I have two questions. So one is, can a protocol, can these tools be used to also detect opportunities for optimization in the sense of you have a protocol and the sort of, like, I don't know, hash version or whatever, and iterate, more and more complex it becomes and affect performance. Other but these tools have opportunities to detect redundant components.
Right. Yeah, that's a good question. So I personally, it is also a evidence for the difference in the only workers. I'm not a protocol person necessarily, but so I think definitely you use them for detecting redundancy or optimizations, and definitely in the fact that you can sort of model your optimization and run the tool against the. So this is a bit of cheating, yeah. But so I don't really know if you can. So this is mostly focused on security. Yeah, I'm not really sure if you can effectively use them in a lot of cases for automatically detecting optimizations. Probably then it sounds like it should be reasonably, but I think it should be doable, but in certain cases at least. But yeah, I'm not too sure if that's a systematic way that people do this. Yeah. So.
Yeah, just curious. I mean, you can't do research. It sounds quite often. The second question I have is, question. So these tools, when you have to prove to show that the secure zone, you kind of rely on these tools to be correct and have no buttons on. Which sounds like a perfectly wrong, but it doesn't exist. And there are no cases where people make some proofs that turn out to be enhanced due to like bugs in these tools.
So actually, this is a very good point. So obviously this is a concern, yes. And the way people like to design these tools is that you have this sort of very small kernel that is trusted, for which the rest of the tool is built. And so you have a small block to verify. And if you use a tool, of course, like many developments, the trusted part remains the same, right? Because all the sort of amplified over the normal proof, right? But to answer what actually the question whether these bugs have been found and used for proving, I am not sure of any specific example where a human made a proof relying on a working tool and thereby was sort of accepted. But in recent times with AI progression, people have been using AI with these formal proof. Because I mean, it makes a lot of sense conceptually. Like you use AI to get this proving. So you like use AI to do the proving for you, and the tool actually gets the AI didn't produce for. So this is like a very sort of nice direction. But then the AI actually tries to be smart, and like it's hard to actually prove it. Let's look at the source of the thing and try to find out. So AI tries to sometimes be better and find bugs instead of actually doing the proof. And so there have been a couple of cases like this, but for human made proof, you're actually just trying to follow the logic of the proof. I don't know any specific actual cases where the proof went through because of the bug. There hadn't been bugs discovered, but then they were fixed and the proof still went through.
What movement is like a specification, let's say, given a specification which should be correct, but then the proof will actually incorrect it. So not like a wrongly specified proof, really the execution of that proof is going to be incorrect, and just invalidating the completeness. So I'm concerned about bugs and probability or tampering are not in the actual written or derived proof. So you're cursing the tool, like you're cursing tampering to execute correctly. Let's say your proof is like 1 + 1 = 2, or 1 + 1 = 3, you write, you write 1 + 2, the tool does something completely different.
Okay, but the statement is so correct, no? But let's see. But what was the question exactly? So you write a correct statement and
or you write an incorrect statement, but the tool tells you correct. Sorry, 1 + 3.
Oh, okay, yeah, makes sense. Okay, yeah. This is exactly the thing that I was talking about. You have like a tool which obviously software containing bugs, but you try to sort of minimize the trust service that you have to have a focused specific point of needing to verify, and then this is the only trust part. Yeah? So if you find out, you obviously need to fix that. But yeah, and so also not all. This is also the most extreme case, and not that if you find like one bug, this sort of ruins the whole logic of the whole tool. Anything else to be typically bugs are just like very minor things that you need to abuse. If it's even like a logic bug, then you need to abuse to get to a point where you can use it to actually prove something that is incorrect. Right? So this is just sort of the, but I mean, there's always this trust. Cool. Yes, you know about that.
Okay, great. Yeah, kind of past schedule. So now we start our coffee break. First of all, everyone has a special diet order. You can find instance, the registration of the special food. And also, since we are a little bit late now, due to the initial delays, so we start at the end of the coffee break, a new session and the natural fees. So, yeah, nice coffee break.